Hi, and welcome to Thermodynamics for Educators, Week 2 Mini Lecture 1. In this lecture, I'm going to make some points about the microphysics of the ideal gas and discuss briefly the introduction of statistics into physics and what horse kicks have to do with that. So I want to briefly review a rough derivation of the ideal gas equation of state from a microphysical point of view, considering the microscopic particles, atoms, molecules that make up a gas. And we're going to make one important assumption in this derivation. We're going to assume that all of our particles are moving at the same speed in each direction. So the components of their velocities in the x, y, z directions are all the same. So let's consider a gas in a box, and we'll just consider one dimension of the box. So this is the left-hand wall and the right-hand wall of the box, and we've got a particle moving to the right. It hits the wall, bounces off, and moves off to the left. And we assume it loses no energy during this collision with the wall. The momentum of the particle just before it hits the wall is its mass times the x component of its velocity. Just after it hits the wall, it has the opposite x component of the velocity, so its momentum is minus mvx. So that means the change in its momentum is 2 mvx. Now, the pressure on the sides of the container arises by the continual bombardment of particles bouncing off the sides of the wall. So how often does a given particle make a collision with this wall? Well, suppose the width of the box in the x direction is Lx, then the time taken for this particle starting at the right-hand side of the wall to move to the left side and come back to the right-hand side is just 2Lx over Vx. The distance it travels is 2Lx and it's going at a speed Vx. Force is just change in momentum over change in time. This is Newton's second law of motion. So if we divide delta P by delta T and we multiply by the total number of particles in the box, that we find that the force on the walls of the box is N times mvx squared over Lx. The pressure is force over area. Well, the surface area of this side of the box is Ly Lz, so force over area is given by this expression here. Lx, Ly, Lz is just the volume of the box. Ly and Lz, remember, are the dimensions of the box, of this face of the box. Rearranging this, we get PV is equal to N mvx squared. So now we bring in the fact that this is just the x component of the velocity. The velocity itself is Vx squared. The square of the velocity itself is Vx squared plus Vy squared plus Vz squared. This is just Pythagoras' theorem. And assuming that they travel at the same speed in all directions, then we can write this as 3 times Vx squared. So rearranging this, we find that Vx squared is V squared over 3, and we can write that pressure times volume is the number of particles in the box times their individual masses times the velocity squared over 3. Now compare with what we get from experiment. Experiment tells us that PV equals nkt. So comparing these two expressions, we find that nkt must be equal to n mv squared over 3. And the kinetic energy, the total kinetic energy of the gas, is just the number of molecules, n, times the individual kinetic energies of each molecule, which is a half mv squared. So using this, we find that the total kinetic energy is 3 halves nkt. The total kinetic energy of the gas is what we call the internal energy of the gas. It is the energy that is available for doing work and transferring heat. So this is a very important result in the history of thermodynamics. It connects the temperature of the gas directly to the kinetic energy of the molecules. The temperature is a measure of the total internal energy of the gas, the total kinetic energy of the gas. So for an ideal gas, there are some very important things that you should always remember. So the internal energy consists of the kinetic energy of the gas, and it therefore only depends on temperature. It's very easy to forget this, and it is very important to remember. The internal energy of a gas, U, is only dependent on the temperature of the gas. The temperature is a measure of the kinetic energy of a gas, of the molecules in the gas. It is not a measure of heat transferred from or to the gas, which is one of the common misconceptions that students often come into classes with. Okay, now This factor of 3 here comes because we had to divide by 3 over here because there were 3 components of velocity. Thinking about that a little more deeply leads to a very profound and useful result. Suppose, for example, that the gas was not 3-dimensional, it was only 1-dimensional. The molecules could only move left and right. So there's only one component of velocity. In that case, the particles that can only move in this direction, their total kinetic energy would be a half mv x squared. And in that case, the total kinetic energy of the gas, the internal energy of a gas, would not be 3/2 nkt, it would be 1/2 nkt. If the gas were allowed to move in 2 dimensions, so you also had a component of velocity in the y direction, then the internal energy would be 2/2 nkt, which is just nkt. We live in 3 dimensions, and our gases mostly are allowed to move in 3 dimensions. So we have the z direction available as well, and that means that the total kinetic energy, the total internal energy of the gas, is 3/2 nkt. These motions in the x, y, z direction are called degrees of freedom. We say in this case that the ideal gas has 3 degrees of freedom. Now, up to this point, we've been assuming that the particles are just little tiny billiard balls, little tiny spherical objects moving about. But in real life, gases are made up of molecules with more complex shapes. For example, oxygen and nitrogen are gases comprised of molecules that contain 2 atoms chemically bonded together, which we can schematically draw like this. So we have the two atoms, and they are connected by what I've drawn here as a little spring to indicate the chemical bond. That means they have an additional number of degrees of freedom open to them. This molecule could rotate, could spin around this axis, the x-axis. And in that case, it has an additional type of kinetic energy, a rotational kinetic energy, given by a 1/2 I omega x squared. I is the moment of inertia of the molecule, and omega x is the angular velocity about the x-axis. Following on from this logic, you can show that this contributes another 1/2 nkt to the total internal energy, bringing the total up to 4/2 nkt. But it doesn't stop there. The molecule can also rotate about another axis. Okay, it can rotate. This rotation is into and out of the screen, and that contributes another 1/2 nkt to the internal energy. Now you might think, well, it can also spin about its axis, but because it's symmetric about its axis, that doesn't count as a degree of freedom for reasons that really require quantum mechanics to fully understand, so we'll have to accept that statement for the moment. Finally, this molecule can move in another way. It can vibrate. It's a spring, so if you pull one of these particles back and let it go, it will bounce backwards and forwards like this. And the energy associated with that is a 1/2 k sub s x squared, where k is just some constant, which is like the spring constant in an ordinary spring. So this comes from Hooke's law of springs, but it applies just as well to molecules whose bonds can be modeled like a spring. And x is the separation between the 2 atoms in the molecule. So this is an additional degree of freedom, and that brings the total internal energy up to 6/2 nkt. So if you have a gas of oxygen or nitrogen, then it could have a total internal energy up to 6/2 nkt, which is 3 nkt. Now, it's important to note that these degrees of freedom are not available all of the time. At low temperatures, the molecules tend not to spin or vibrate, they just move translationally in the x, y, and z directions. And so at lower temperatures, the total internal energy would be 3/2 nkt. But then as you crank the temperature up, the molecules will start spinning, and you'll start adding in these extra degrees of freedom until at high enough temperatures, we'll find that the internal energy will be 6/2 nkt. In general, because we don't want to specify absolutely how many degrees of freedom we have when we're figuring things out, we will often just label the number at the top F, where F is the number of degrees of freedom. So it is 3 at low temperatures for translational motion, and it can be 4, 5, or even 6 at higher temperatures. This results that each of these degrees of freedom, which corresponds to a type of energy that depends on the degree of freedom squared, is called the equipartition of energy. Okay, let's move on to discuss a couple more things about this model. Now, this is an example of this example that I've just given you, the derivation of the ideal gas equation from microphysics, was the first example, the first result in a new field in the mid-19th century called kinetic theory, which has the following assumptions. It assumes we can apply Newton's laws to the motion of microscopic particles. It assumes particles collide elastically with each other and the container walls with no kinetic energy loss in the collisions. It assumes there's a large number of particles and that their separation is large compared to their size, and that the distribution of speeds doesn't change with time. And this final one is something I'd like to comment on a little more. What is the distribution of speeds? Well, in our simple derivation that I've just been through, we assume that they all moved at the same speed. That means, to use technical language, they are described by a probability distribution function which has only a single value at one value of the speed. So let's discuss what that means. We're familiar intuitively with some simple probability distribution functions. Take, for example, flipping a coin. Okay, we know that if the coin isn't biased, there'll be an equal probability of getting heads or tails. So if we plot the probability versus the outcome, so the outcome can be either heads or tails, then at heads, the probability is a certain value, so it's just a single thin line that goes up to whatever probability there is of getting heads. And at tails, you've got another line and it goes up to the same value because we know that the probability of getting tails is the same as heads. And we can call this probability a constant. What is the value of that constant? Well, we all know intuitively, but it's useful to understand where this intuitive notion comes from. So we know intuitively that it's a 50-50 chance of getting heads or tails. The probability is a half for each outcome. That comes about because we know that when we add up the probability of every possible outcome, we have to get 1. We can't get a probability greater than 1 if we take into account every possible outcome. We know that 100% of the time, it's either going to be heads or tails. There isn't any other option. So mathematically, we write the sum over the outcomes of the probability is equal to 1. Okay, this big symbol sigma just says add up all the possible values of the probability corresponding to all the possible outcomes. So if you do that, here the probability of heads is c, and we add that to the probability of tails, which is also this constant c. So the sum over p is equal to 2c. Well, that has to be equal to 1, and therefore rearranging that, we find that c is equal to a half. So we get back what we already intuitively knew and seems obvious to us. Okay, slightly more complicated, but still very obvious and familiar to us, is rolling an unbiased die. So we know again that there are equal probabilities of getting 1, 2, 3, 4, 5, and 6. These are the possible outcomes. Therefore, for the probability to fulfill this criterion, that the sum over all the outcomes of the probabilities is equal to 1, that tells us the probability of each outcome must be 1/6. Then when you add up all 6 of them, you get 1. Okay, so let's think about what we just did with in our derivation of the ideal gas from a microscopic analysis. So what we implicitly assumed is that out of all possible values of the velocity that the particles in our gas had, they all had one single value of the velocity. They all had the same value. What that means is that the probability of finding a particle with a particular value of velocity is just a single line at that value of the velocity. So it's equal to 0 down here at smaller values of velocity. It's equal to 0 up here, and it's equal to 1 only at this particular value of the velocity. We know it's equal to 1 there because when you add everything up, it has to equal 1, and since this is the only contribution, that has to be equal to 1. So this was our approximation. Now it turns out that in real life, the particles in a gas have a wide range of velocities, and the actual probability distribution was figured out by James Clerk Maxwell and was later generalized by Ludwig Boltzmann, who we will encounter many times in the next few weeks. And it looks like this. This is the Maxwell-Boltzmann distribution of velocities. Okay, so you can see that the probability of finding particles with a given velocity is not 0 anywhere. In fact, there's a tiny, tiny probability of finding particles with velocities at very high values here. But it does peak around here at a most probable velocity. Now, it turns out that the ideal gas equation that we derived doesn't change even though we've made the wrong assumption here. But there are some things that do change when we actually use the correct distribution. For example, certain chemical reactions For example, certain chemical reactions only occur when particles collide together with very high values of velocity, much higher than a value that we assumed here. So in this simple model, this would predict that those chemical reactions don't occur. But in our laboratories, we see that they do occur. And that's explained by the fact that there is a small fraction of particles with high enough speeds to allow those chemical reactions to happen. So in our assumption, it was trivial to add up all the contributions to the probability because there was only one. Now, what do we do in the Maxwell-Boltzmann distribution case? We don't have discrete outcomes. All values of velocity are possible. This is a continuous function. Well, what does it look like when you add up all the parts of a continuous function? Well, in mathematics, we call that integration. So this expression here, this requirement that all the probabilities add up to 1, looks like this now, that the integral from a velocity of 0 right up to a velocity of infinity of all the probabilities at a given velocity is equal to 1. That's the criterion that we have. And later on, we might get into how we calculate this integral in the case of a Maxwell-Boltzmann distribution. For now, I just want you to see the expression and understand what this expression means. Now, another thing that we can do with probability distributions is find the average. What is the average outcome, for example, on a dice? Well, we know how to figure that out. We multiply the outcome by the probability of that outcome, and then we add them all up like this. And if we do that, you can do it in your head or on your calculator, you'll find that the average outcome of rolling a dice is 3.5, okay, which is right in the middle here, which is kind of intuitive. Of course, it's not an outcome that you can ever get, but on average, if you roll a dice 100 times and divide your results by 100, you'll get 3.5 there or thereabouts. So this is the average. Mathematically, this is written like this. It's the sum of overall the outcomes of each outcome times the probability of that outcome. So here, for example, the outcome is 6. The probability of the outcome is 1/6. And so this means multiply 6 by 1/6. And then we sum it up. So we add it to all the other products of outcome with the probability of the outcome. And then we call the average the outcome in these angled brackets. So that is the notation that we use to denote the average. So the average speed of molecules in the Maxwell-Boltzmann distribution, which we call V in angled brackets, is this time equal to the integral from 0 to infinity of the velocity times the probability of finding a particle with that velocity integrated over all the velocities from 0 to infinity. And if you calculate that, you'll find that it comes out to about here. You can also find the average of the square of the velocities. All you do is, instead of multiplying all the probabilities by V, you multiply it by V squared and integrate. And this is called the average velocity squared. And that is found to be slightly higher than the average velocity. And our approximation earlier actually amounted to replacing the distribution of velocities with the average velocity squared, which you can see if you look back at our equations, we found that that 3/2 kT was equal to the kinetic energy of a given molecule. Well, what we were actually doing was assuming that it is equal to the average kinetic energy of the molecule, which is 1/2 m times the average value of V squared. So in real life, this is what temperature actually means. It's a measure of the average kinetic energy of molecules in a gas. We will come back to these results later on. I just wanted to give you a first glimpse at probabilities and statistics. Let me give, on a final slide, a quick history lesson. The Maxwell-Boltzmann distribution was really the first time statistics had been applied to physics. Statistics existed before 1860, and it was the study of the state. Statistics literally means the study of the state, where by state we mean the country, a large population of people. And it was studied out of practical necessity. For example, if your country has an army, you want to know how many uniforms do you make in each size. So you want to analyze the distribution of heights of soldiers in your army. Famously, the Poisson distribution, which is an important probability distribution, was discovered when Poisson was analyzing the statistics of how many soldiers die of horse kicks each year. And it was Poisson who helped bridge the gap between statistics and physics and helped introduce statistics into physics.